All right, everyone, I would like to welcome Bob Cappetta. You all know who Bob is. I'm not going to give him a bio. He's been with us a long time and has done lots of stuff. That's Bob. Was at, of course, COD for many, many, many years, and now he is at Southwestern, Florida Southwestern College. Is that right, Bob?
Well, hopefully you're seeing it on the screen. Is it there?
Oh, there it is, Florida Southwestern State College.
There you go.
Anyway, I introduce you guys so for someone's going to tell you a lot about his favorite calculus problems, I hand it over to Bob Cappetta, folks.
Thanks, Mike. Are you able to send people to breakout rooms, Mike?
I can.
All right, so we're going to do that occasionally today. So we have, what, 15 people in the room is what we have? So maybe send them to set up groups of 4 for me.
You bet.
Sound good?
I can do that.
All right. We need to move. Here we go. Here is a question that I first came across when I was working on my dissertation 100 years ago. And Annie Seldon's theory is that students never really learn how to do calculus. They can never do non-template problems, non-routine problems. So here's a nice one that I'd encourage you to look at. And it's relatively easy to do with L'Hopital, but a little bit harder to do otherwise. So, you know, when you get bored in the next hour and you want to work on that problem instead of listening to me, you have my to do that instead of going to eBay or Amazon.com or CNN.com or wherever else you go during Zoom meetings. So there's a problem for you to work on. I have a solution worked out at the end of the slides that I'll make available when we're done. So here's our first question. So what are the characteristics of a good calculus problem? So Mike, I want 2 minutes, just a quick 2-minute break. Send people to the breakout rooms for 2 minutes and we'll come on back and talk about it.
All right.
Let's see if that works.
Bob, I'm sorry. That was the first time I've ever done a breakout room, and you were there a little bit longer than 2 minutes.
Fine. We had a great discussion in our group. So yeah, we talked about, you know, what makes a quality calculus question, a good calculus question. And some of the notions that we came up with, Michael Farquhar mentioned, teasing out conceptual understanding. You know, so how can you ask questions that do that, but recognize that that might actually cause anxiety in the students. So that's a little bit of a concern. We talked about focusing on concepts, especially spatial visualization. You know, so that if you're going to look at these things, it's got to make sense to you in multiple perspectives. We want to do our best not to just go with rote problems, as well as connecting ideas. These are things we talked about. If you have others, kind of throw them in the chat. So if every group could have 1 or 2 things that you talked about, throw them in the chat. I will have Mike share them with us shortly. And I'm going to go ahead and pull up my screen again if I can find it. PowerPoint, here we go. And we'll go to the next question. So here's what I had prepared. Difficult for technology to answer. Now, I've thought a lot about this talk in light of what Maria said. Because what we heard at her main talk was, let's use the technology to solve these problems and get away from some of these rote procedures. I don't think I'm with her 100%. I think technology is a good tool, but I'm not quite yet ready to say that we can just offload everything to technology. This has been terribly important with the COVID crisis so that we can write assessments that actually measure something other than their skills on Google. Design questions that encourage students to reflect on concepts. So that sort of came up in our group. Give students opportunities to demonstrate that they truly understand concepts, definitions, theorems. Just because you can state the theorem or the definition doesn't mean you can use it, doesn't mean you understand it. So I believe we can ask questions that get at that. This is a big one. And this, I think, goes back to the Annie Seldon question I showed you. Require students to solve types of problems they haven't seen before. That's a goal that I always have. Now, this is a big one. Too many students throughout the curriculum think every math problem should be able to be solved in 5 minutes. The only way we're going to change their minds if we give them some problems that take longer. Now, I'm not saying put it on a 50-minute exam, give them a problem that takes 20 minutes, but on a homework set for sure. I think it's important for us to do that. And of course, show them why calculus is relevant. So can we give real world situations that are more than just contrived word problems? I would hope so. All right, here's one I'll just ask you to answer in chat. What do you think are the differences between problems and exercises? And rather than saying, is it possible for a problem to become an exercise, why don't we change it since it's a chat question? How does a problem become an exercise? So I'll give you maybe 30 seconds to answer that in chat. So go ahead and quickly write something down. Okay, Mike, let's see. I don't think I can see the chat, Mike, so I'm going to have to lean on you. Can you read some of the good suggestions?
We had one that said, an exercise is routine, a problem makes you think.
Okay.
We had, oh, now they're really coming through. Let's see where I lost my spot. Oh, problems are more involved. Exercises are more algorithmic, almost busy work. That's kind of very close to what I almost typed in. A problem becomes an exercise when the solution is applied by rote. If you don't have to think about how to solve it, you're just practicing the technique. It's an exercise.
I like that a lot.
I think exercises are more routine or assess basic kinds of skills. Exercise is a quick problem without context. A problem is a longer, more in-depth with possible real-world context. Okay, questions that have them tie concepts together would be problems.
Okay. Well, there's obviously different definitions to different people, but I think we're getting at the key theme. This is what Schoenfeld says. Procedural understanding, I think, is a big part versus conceptual understanding. Focusing on non-routine problem solving, it's not quick and easy. So here's one. So this is what I would say is an example of a problem. Why? Real world application, that might be a stretch. But it does require you linking a couple different concepts together. It's not applying one rote procedure to a problem. You've got to think in a unique way to be able to solve this. So I've quickly worked this one out, although I want to give you maybe another 10 seconds to think about how you get it started. Because I do think this is a nice little problem. So here we go. Sum of n goes from 1 to infinity of b to the log n. What do I do? Well, I want to rewrite b to the log n. So z is b to the log n. Take log of both sides. Log z is log b to the log n. Then the log n comes down front. You see what's going to happen, don't you? So log z is log n, log b. So e to the log n, log b is z. That's e to the log n, log b is z. N to the log b is z. I thought that was really cool when I saw that for the first time. That b to the log n was the same as n to the log b. It's kind of obvious to me now, but it certainly didn't feel that way. So if we want to go ahead and find out when this converges, that's a relatively straightforward use of the p-series test, right? Sum of 1 over n to the negative log b. Negative log b is our p. So we need that to be greater than 1, so b is less than 1. So I would argue that's a problem. And I would argue that it's important for us on occasion, now not on every test, not on every problem, but to on occasion push students to be able to do these kinds of things. Here's another one. We're in a course, I assume this is Calc 2, to examine the integral from 0 to 1/2 of 1 over 1 plus x cubed dx. Now this could be a problem, this could be an exercise. If you don't tell them how to do it, I argue it could be a problem. If you tell them use a series, then it becomes an exercise. It is nice. I mean, this is relatively easy, of course, right? First term over 1 minus the common ratio. So the first term is 1, common ratio is negative x to the third. Write it as a series, integrate, and evaluate. And that's what we get. And you can see just how good this is. I went out to that power. I did the integral on my graphing calculator, and you can see I'm good to 4 decimal places. So that's pretty good. Pretty good approximation. But what is also important about this, another thing I like about it in terms of reflecting on it, is looking at the interval of convergence. I have this integral going from 0 to 1/2, which is inside that interval. So a nice follow-up question to this would be, is can you do this for the integral from 0 to 2? So we can take what might be a relatively easy problem and make them think in terms of reflecting about what it means by going beyond that endpoint. All right. Now, what do you think about this? Does anybody have a strategy? I'll throw it to the floor. Either, send Mike a note or speak out loud. How would you approach this to find the derivative of the inverse hyperbolic cosine of x? And an answer of I don't care what it is not acceptable, although I don't necessarily disagree. Who has a strategy of how you'd approach this?
We could perhaps use the definition of hyperbolic cosine with e to the x.
So a hyperbolic cosine is e to the x plus e to the negative x.
Negative x over 2, is that right?
You're saying maybe try to solve for x? That might be tricky. There's one, I think you could get there, but there's one other idea that I'm looking for. Anybody? Well, my tool is the implicit derivative. So y is the inverse cosh of x. So cosh of y is x. So derivative of cosh y is the derivative of x. So sinh y dy dx is 1. Again, is this the most important question you're going to ask? I don't think so, but it's a nice application of how we can use an implicit derivative to find the derivative of a challenging inverse function. And then here's our fundamental identity in the world of hyperbolics, right? Cosh squared y minus sinh squared y is 1. Cosh is what? Is x. Cosh y is x. So x squared minus sinh squared y is 1. X squared minus 1 is sinh squared y. Sinh y is actually square root of x squared minus 1. So another question I would ask in the middle of this is why is it positive and not negative? So I'll let you think about that. What tells us that we need the positive version of that? And then once we have that, of course, dy dx is 1 over sinh y. So dy dx is 1 over the square root of x squared minus 1. So again, I think this is nice, showing you, and we know all the tools to use the implicit derivatives. In fact, I use this technique for the derivatives of all the inverse trig functions, which most of us have memorized. But since I didn't think we had this one memorized, this was a better example to use for this presentation. All right, let's keep on keeping on.
Hey, Bob.
Yes.
I think on that last one, it may be a good problem that you could prompt your students by say, find this derivative using implicit differentiation.
I certainly would do that in class for sure. I would.
Yeah, because that would at least hopefully might be able to give them a little bit of a nudge to go into that direction.
I hope one of my colleagues would have come up with that, though. That's it. Now,
Chris basically got it in the chat.
Right. Of course, Chris got it. I'm not surprised. Now, this is one of my pet peeves, is when problems become exercises. And I'm guilty of this sometimes. We all know the formula for maximizing the area of that three-sided region, the farm adjacent to a river. If you do that problem 2 or 3 times in class and then put it on the exam, it's an exercise. It's no longer a problem. Same thing with the ladder sliding down the wall. If you do all the modeling, right, you show them what the variables are, how they all fit together, and then the analysis you need to use, it's no longer a problem. Now, is there some value to that? Of course. But be careful, be careful. If you're using delta epsilon strategies, you can do that, but you can turn that into a process. Same thing with Riemann sums. You can have a formula, right, for the distance between parallel planes, but wouldn't it be better to kind of use vectors and projections and such to see how that works, to think about it, piece it together rather than reducing it to a rote rule? Same thing with integral of something like cosine squared, which is relatively easy to develop from the identities, but a lot of students just memorize it. So I'm just asking you this. As you are writing your challenging problems, make sure you're not doing them for the students first and having them repeat it so that the problem becomes an exercise. I think that's a concern. All right, so here's one goal that I have. We want to identify faulty reasoning. So this I find very powerful with undergraduate students, with first-year college students. So here's a famous question, the integral of 1 over x dx. And we know how to do it. Maybe we have it memorized. That's great. But what if the student wants to do it with integration by parts? So I have the integral of 1 over x dx. I have u and I have dv, right? So u is 1 over x, dv is dx, so you get the idea. So this is uv, 1 over x times x, fine, minus the integral of v du minus a minus, so plus v du, integral of 1 over x dx. You see that? Well, do you see what's going to happen here? What's our issue? Integral of 1 over x dx is 1 plus the integral of 1 over x dx, which of course most students would say subtract the integral of 1 over x dx and you get 0 equals 1. Now, why do I like this? Now, granted, this is integration by parts, so this is fairly long into the discussion of integration. Students need to recognize that this is a family of functions. They need to add c. So when my students forget to add c, I always ask them, what's my last name and what's the first letter? If my last name is C, this thing's last name better be C. But hopefully this is one of those experiences that convince them that's something for them to think about. Here's another one, a faulty reasoning problem that I think is interesting. Let's say that S is the sum as n goes from 0 to infinity of 2 to the n. So 2 plus 4 plus 8 plus dot, dot, dot. So what is 2s? Well, 2 times that. So 4 plus 8 plus 16 plus dot, 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 dot. So how about 2s minus s? You see all of these, you see all of those. What is 2s minus s? What is it? It's negative 2.
I'm sorry, Bob. Shouldn't that be 1 plus 2 plus 4 plus?
Oh, did I miss it 1? Yeah, I did. Whoops. Well, thank you very much. Or I could just change it. I have an easier
n equal 1. N equal 1.
There you go. There's my type 1. Easily fixed, more easily fixed. That's right. So if we make it a 1, this is still equally ridiculous, right? So we're saying 2 plus 4 plus 8 forever equals negative 2. Obviously, that's crazy because we're not looking at the partial sums. And too often when we teach things like the telescoping series, we don't make an effort to look at the partial sums. We don't look at the limit as n goes to infinity of s of n. So this is what I would start with. I would start with this sort of a discussion and say, where is this falling down? Where is this a problem? And then use that to motivate the discussion of the partial sums. Okay, Mike, 2 minutes. Back to our groups, please. What do students say about calculus after they complete the first course? So if you would please, back to our breakout rooms. Well, we're back.
On that one.
Sorry?
We didn't get a countdown warning on that one. It just cut us off. I would talk to the presider about that.
It happened fast.
Yeah.
All right. So let's see. Omar, I'm going to ask you to say something. If you can unmute your button. What do you think students think at the end of their first semester of calculus, Omar?
Yes, what I was saying is if they're in my experience teaching it, I often have students who are surprised at how little calculus they learned in high school when they thought they had calculus 1 already in high school, and they find out, wait a minute, I didn't learn what I was supposed, everything I was supposed to, especially at Jim mentioned about the theoretical underpinnings, the fundamental theorem, the mean value theorem, things like that.
Very good. Caroline, what can you add? What do you think students think when they finish their first semester of calculus?
How much they should have paid more attention to their pre-calc. Seems like the pre-calc portion is harder than the actual calculus, but sometimes they're so unprepared that that's what's, giving them a hard time in calculus. So
in a lot of ways, that is absolutely true. All right, well, let's take a look at some of the things that I put together. This is what Lynn and Kessel say. They believe the calculus courses are designed to discourage mathematics study. Way, way, way back in the mid-'80s when I started my career, Tucker published a book called Calculus, a Pump, Not a Filter, to try to argue that we needed to change the philosophy that calculus was designed to get rid of folks who should not pursue degrees in science and technology. And we should redesign it so that we can encourage more to do that. Yet 10 years or so later, Lynn and Kessel noticed that really hadn't been happening. They also noticed that students switch out of math, people who wanted to study mathematics after calculus. Now, this doesn't particularly surprise me because calculus is not really mathematics. I very much enjoyed mathematics. I didn't really care much for first year calculus at the University of Illinois in the 1980s. And that was not necessarily a good experience. So I get that. So it needed to be redesigned. Students usually say the instruction was bad. So sorry to say, a reflection on our profession, you know, some 25 years ago. But the saddest part is that it's the best students who leave math after calculus. So I mean, there's no doubt there was a crisis then, and I think little has changed since. Annie Selden, she's the one who had the limit problem that we looked at before. She shows that they can't do non-routine problems. She also shows that they recall very little in later classes, very little calculus. And another thing that I really like about her research, she busts the myth that students learn the stuff from the previous course when they're in the next one. At least as far as non-routine problems, that was not the case with her research. And here's Park and Travers. I believe that's Ken Travers from the U of I. I'll let you quickly read that in terms of suggesting where we should go.
Bob, you're not screen sharing. I can't see your screen.
I'm not screen sharing. Thank you. Let's screen share. And I need to do that. So I need to go back to Zoom. I need to screen you. Matt, you are a true friend. There we go. Screen share. And play from current slide. So we've gone there. So again, what I talked about Lynn Kessel, talked about Annie Selden, and here I'll let you read Ken Travers' stuff.
Bob, I think one thing that the developing that meaningful problem solving abilities and things, one thing that I try to get my students to and also help to remind them is when we're doing like the trapezoidal or Simpson's rule, and we're doing the part where you're finding the value of n you need to meet the specific tolerance, and it's got that maximum of the absolute value of the second derivative or the maximum of the absolute value of the fourth derivative, that's a perfect place to bring in the extreme value theorem of a continuous function on a closed interval, and not just have that be at the endpoints, but maybe have it be something that is where they have to find the critical values of the second derivative or the critical values of the fourth derivative. And also think not which one gives out the biggest number, because it's the absolute value, right? So it has to be which one is the most extreme away from the x-axis. You know, so like, some of those things, I mean, they're just waiting to to like delve into a little bit more and say, see, we did this back then, and maybe it was an exercise back at that point, but now I can embed it in a problem.
Very good. Yeah, putting it all together. That's great. This is what NCTM said back in '91, again, with principles and standards. And I really don't know that we do that a whole lot as first-year calculus teachers. I don't know if that's really part of our culture. Can it be? That's something for us to think about. All right. So here's what I call exploratory questions. So we looked at the identifying the faulty logic. So another set of questions I try to build are exploratory. But I want to be careful with this because this is not formal mathematics. If Sunil were here, I would make sure that I quote Wu, because Sunil Koswada from Harper is a student of Wu. Wu has some real problems with calculus reform and math reform in general. And I respect his concerns, but I think there's also something to be said for studying these heuristics. So for example, use Desmos to demonstrate that the derivative of sine x is cos x. So how do I do that? How do I expect my students to do that? With something like this. Okay, graphing sine x, which is in red. Graphing using the difference quotient now, right? Okay, so we're connecting the difference quotient to the graphs. F of x plus h minus f of x over h for a small h. What we have in blue is an approximation, but a pretty darn good one, of the derivative of what we have in red. And if you recognize the blue function, you can see indeed that is the graph of cosine x. This is most certainly not a proof, but I think it's a valuable insight in terms of helping students connect ideas. Here's another thing that I really think is fascinating that I would encourage you to share with your students, right? The area of the circle is pi r squared and the circumference is 2 pi r. And the derivative of pi r squared is 2 pi r. Same kind of thing works for volume and surface area. Why is that? Why is that? And you know, I do have a citation here that I will post the PowerPoint or the PDF in the chat here before we're done, so you can look at it. But it's a nice look at the differential in terms of how it behaves. Here's another thing that I like very much that I don't necessarily see in a lot of places, and that's reflections on definitions and theorems. So students can state things not really know what they mean. So take a look at this question. Can anyone guess what concept I'm trying to get them to look at here? Any ideas?
We have concavity in the chat.
That's not what I had in mind,
Yeah.
but it certainly could be there. Anybody else?
Critical points?
Your critical points and like well, your max mins or.
Exactly right. Critical points, max mins, first derivative test.
Mm-hmm.
So, and here's another version of that they always get wrong. I could say it is not a graph of y equals f of x in bold, in red, in giant font. It doesn't matter what I say, they still think this is a graph of f instead of f prime.
So I do where I like graph a polynomial looking function, it's f prime of x, and then go through and you have to graph one of the family members of f of x. And one of the things I do is like have them fill out a table similar to when you get all of the information, but then I actually have this screen that I can pull down and cover up the graph, and I make them write out what all of the characteristics are of f of x, and then let them look at it again. They can't not look at f prime of x and think it's you know what I mean? So I make them cover it up after they get their table. Yeah.
That is great. Yeah, thinking numerically is certainly a wonderful tool for this kind of problem. Here's one. Again, I would like to give this to them before L'Hopital. Right? You know, you do a few problems and you get a feel for it, but can you go back and reflect on it? Can you reflect on what it means? So this is one I like. I'm not a big fan of multiple choice questions, but they do come in handy once in a while. Okay, so I hope it's obvious that what I'm getting at here is the intermediate value theorem, right? So as we see the sign changes, where are the zeros? So between -6 and -3, the function must have a 0. No, but it might have a 0. So I could ask a different question. The function might have a 0 on the interval from -6 to -3. Yeah, that's a little confusing. But the function must have exactly 2 zeros from -6 to 4. Well, it'll have at least 2 zeros, right? So there's different fun things you can do with this to get at that concept.
Hey, Bob.
Yes.
I think in that one, a lot of students still think discretely. And so I think that's a good example to try to get students to stop thinking discretely and start thinking more continuously.
Yeah, I did say this is a continuous function. I probably should have made that in a bigger type font.
Yeah, I'd never do it on a exam, but I sometimes when I teach calculus, I'll change part A to say the function could have a 0 between -6 and -3, just to, you know, and then of course I'll draw like an absurd example that shows whether it could or not, and they kind of tries to get them to think outside the box a little bit. But I would never be that cruel on an exam. It depends upon my mood when I'm writing the exam.
I really want them to understand these theorems, and I think these sorts of questions help with that. All right, who can answer this question for me? Can I throw this out to the room? The virtual room? Why is that? Who has answered?
It's not one-to-one.
Well, that's our issue.
Yeah, G of X, right.
So we want to use calculus to prove that it's not one-to-one. Why is that?
Something about the derivative changes sign for G, but it does not change sign for F.
Perfect, yes. F prime is 6x squared plus 5, always positive. F is strictly monotonic, it's increasing.
You sure it's not one-to-one? All you need is one counterexample, though. You don't need calculus.
That's not calculus. Jim, you can't change the rules. I'm
Oh, I'm sorry. Oh, I didn't know.
I say you can answer a different question, you know, in your class. I said use calculus.
I
Absolutely.
understand.
Of course. If a real number C is in the domain of the function f of x, and if the limit is x approaches C of f of x equals 2, then the function is continuous, one of Jim Trefsker's favorite topics. At x C. So what do you think, Jim? Is this true or is this false?
Yeah. I don't like it.
I don't either, because f of C could be something other than 2.
Right.
But will the students see
Three
that?
things.
Will the students see that? Yeah, that's so false.
I have them do the checklist of the 3 things.
Yes.
Here's a question I've been given for years in Calc 2. So these two series are divergent. So is the series defined by their sum divergent necessarily? And the answer, of course, is no. So you construct a counterexample, you know, where one is the opposite of the other. But if you make them both always positive, right, then it is.
Oh, yeah.
So that's something to think about. So this is a good starting off point to ask some rich questions. This is a little similar, I think, to, well, not quite extreme value theorem, but gets an idea about how the function is growing, right? So it basically relates the derivative to the growth. Differentiable everywhere. The derivative is always less than 2, so it's not growing fast enough to get to 25. So there, you have to look at that, some analysis, but I like that question. Here is one of my favorites, although I'm not sure it's Wu's favorite, as we mentioned earlier. Explain why integral from negative r to r of x cubed dx is 0, but integral from negative infinity to infinity of x cubed dx is 0. So when I met Wu at Sunil's conference a couple years ago, I asked him why he was so upset with order of operations. Wu's argument is order of operations is a cultural construct. We've decided that multiplication comes before addition, and there's no reason it would have to. And I agree with him. It is a cultural convention, but it sure makes writing polynomials a whole lot easier. The point of the matter is the fact that this diverges is also a cultural convention. We essentially say if one piece of it diverges, the whole thing diverges, but students really struggle with this. So
you mean it's not equal to 0?
Not equal to 0. Right? That last part, you want that not equal to 0.
Oh yeah, not equal to 0. Whoops, there's 2 typos. That's why I do this talk here before I go to IMACC in the fall, so I have all my typos fixed.
Sorry.
Thank you. No. Don't apologize. I really appreciate that. All right, next up. We'll see how this works.
Okay.
It's a fundamental term of calculus question,
Yeah.
right? So, you just have to see how that behaves. Knowledge play with it a little bit.
Prime of cosine x times negative sine.
Yep. And here is another question that gets at the fundamental theorem of calculus and the definition of derivative, how they both kind of fit in here. I guess, you'd have to integrate those 2 things. So coordinating the definition of the derivative and the fundamental theorem of calculus gives you this answer. So that's why I would call that a rich problem, connecting 2 disparate ideas. I also like problems that ask students to construct examples. I know we're getting a little short on time here, but I'll quickly go through these. Construct a function, f of 2 is 5, f of 9 is 5, but there is no point C on the interval, or f prime of C is 0. Now make it continuous, now make it differentiable.
Oh, yeah.
I'm walking them through Rolle's theorem, or I could do a similar sort of thing with the mean value theorem. But I want them to draw those pictures, show me how that's going to behave. So this one's impossible, right? It's differentiable where that's not going to happen. Something as simple as this is often difficult on the first calculus test. I want a continuous function, whose domain is that and whose range is that, and the log function is the example we have in mind, but they struggle with that. I like that better than just giving them the log function and asking them for the domain and the range. They can look at a graph. I like the process of going backwards a little bit. We've seen these problems forever, right? How do you fix those numbers so it's continuous everywhere? Limit from the left equals the limit from the right. You've seen that. This is a textbook question, but it's still one I like. It's still a question I like. And I can really be evil if I remove the equal sign here, so it's impossible. If the negative one's never in the domain. I wouldn't quite be that. I wouldn't quite be that evil. But
I'm curious if you consider that now a problem or an exercise.
Yeah, it's a good question. I think that's a fair criticism. This might be an exercise. But if I don't give them any hints in terms of how to get it started, it could be a problem.
Just curious.
Here's one that you wouldn't think would be hard, but you know what? They never get this one right. Construct a graph of a function whose derivative is constant but not zero. Most people just draw the function f of x equals 0, which is correct, but not interesting.
Yeah.
If they gave me the function f of x equals 2, okay, that's better. But this one, they've got to give us a line, right? An oblique line.
Yeah, straight line.
Yeah. I think all lines are straight other than a vertical one. No, that's not going to happen.
But you're right, it's got to be oblique. It can't be, yeah, the horizontal.
What do you think about this one, friends? Second derivative is f, but the first derivative isn't f.
Cosine.
Sine,
Oh,
cosine.
no, because we got, that's going to switch sign, right? That's not going to be it, is it?
What do you think?
Someone said hyperbolic sine in the.
There you go.
Yeah.
Show up
Yeah.
one time. Who could believe such a thing? It's pretty hard, depending on when you give that to these students. Certainly low-level students, I don't think have much of a chance on this, but in Calc 2, maybe they would. Find an equation for the following graph. Assume the usual orientation of axes. With this sort of computing technology, I like these things. This is probably from Paul Seeberger, actually. I like his Calc 3D plot. So I want them to visualize these quadratic surfaces. So quickly, some word problems. Here's a nice example of the mean value theorem. Starts at 2 at 4 o'clock. By 4, the car's gone 80 miles. Use a concept from calculus to explain why there must have been an instance where the speedometer went exactly 40 miles an hour. I would like them to say that driving in the car, distance versus time is differentiable. Therefore, the mean value theorem applies.
That's
Like
right.
they never do.
That's one of the examples, and I talk about them going like through the toll gates, and like you can slow down and go the speed limit through this toll gate, but then you speed up and you get to the next one too fast. Technically, you could get a ticket in the mail because they've got a picture of your face, they've got your license plates, and by the mean value theorem, you sped somewhere during that
No, I
span.
like that. That's
Yeah.
nice.
I always say the story that the state police in Pennsylvania actually did that in the 1980s on the turnpike. They actually used the data and gave tickets in the mail, but then of course litigation happened, and they can't use mathematics to give tickets to
Oh,
people.
yes.
So one of our goals is to relate the math to real world, sort of. So here's a cell phone plan. I'm sure you've seen these sorts of things. Limit from the left, limit from the right. Does the limit exist when it's a piecewise function? So just putting it in some context that the students can recognize.
Bob, we started a little late, so I'll give you about 5 more minutes.
Okay, I think I can finish. This question I found in a business calculus book, and I really kind of like it. For each 10-cent reduction in price, 40 more sandwiches would be sold. So I'm sure market research is never quite that simple. But what should you charge for the sandwiches to maximize your revenue? That's kind of a nice little problem. So if you haven't given one like this in your classes, you can add that to your list of min-max problems. And then here is the standard open top box with material costing various things.
Mm-hmm.
Chris, yes, this becomes an exercise when you do a bunch of them like it in class. But if they look at it from the first blush, it's a pretty challenging little problem.
Pretty good.
Proofs, of course, got to have some. I want them to do this, again, thinking of the definition of the derivative.
Oh.
Okay. That's the concept I have in mind there. This, of course, is some variation of the series expansion for sine. This is sine pi over 6.
Yeah.
So again, going backwards to show the sine pi over 6 is 1/2. And I also like to do these kinds of things where I outline the proof and have them fill in the lines to kind of connect the ideas and then use it to solve something else. So this is a pretty challenging one from multivariate calculus that gets at it from the perspective of curvature. So that's, I mean, that's the kind of proof that I like. Of course, I use delta epsilons and Riemanns, but this I think is more of a problem than an exercise. So that's it for me. If you're interested, we've got Annie Selden's answers after at the end of my talk. So let me go ahead and stop the sharing, and I'll open the floor for some questions, and I will see if I can post the file in the chat here.
Jim has a question.
Hey, what's going on?
I just wanted to go back to, you went over it real quickly, the 4/3 pi r cubed and the derivative is 4 pi r squared. You
Sure.
ought to also just, I would also include, the area of a square is s squared and the rate of change is 2s. You got 2, you're going to grow this way. I'm sorry, I'm not making this in the air. And the same thing with the area, the volume rather of a cube is side cubed.
Yeah, that's exactly right. That extends to all kinds of different shapes. Exactly right. That's wonderful. I have posted my slides in the chat. So it's 1.69 megabytes. So you should be able to download that. If not, I'll send it to Mike and he can send it to you.
That's great.
There you go.
Thanks again.
You bet. Other questions?
Have you lost as much weight as I have?
I needed to, Jim. The doctor said, get healthy. And I said, okay, I love to eat. I'm just not eating as much as I used to, which for an Italian is pretty hard.
I've lost 90.
Yes, it is.
90. Bravo. Bravo.
How much? Can you tell me? You look like you might have lost about the same.
Yeah, it's close. We're in the same ballpark.
Okay. Well, that's a third of my body mass is gone.
But 100% of your mind is still there. Chris
I'm
asks,
hoping.
how do we build students up to this? Yes, Chris, that's a great question. I mean, if they've gone through other people's classes in Calc 1 and Calc 2, it's pretty hard to kind of change their mindset in Calc 3. When I was in college at DuPage, I started with Calc 1 and had the same students, 2, 3 differential equations. So they did pretty well by the time we got to the last one. But you've got to build confidence. It's real important. You've got to show them that they are capable of doing these kinds of problems as long as they give it a good effort. And hints, it's always, if they're struggling, then you give some hints. Throw hints out as you go. Collaborative working, I think, is also helpful. But yeah, that's the question. That's a big one.
I have a difficult time doing that in an online setting.
Yeah.
This has been a year long. Oh, goodness gracious.
Yeah.
To keep them apart, like you can't get them working like really close so they're like yelling across to the next desk and can't look, you know what I mean? It's just hard.
I'm worried about that next year. Am I going to be able to let them work collaboratively in the fall, or do they need to be 3 or 4 feet apart from each other? Because if that's the case, I might as well do it online. If they can't even talk to each other, it's a little better being there, but not a whole lot. I don't know. We'll see. Anything else? AP students. Both of my daughters, I'm not bragging, both of my daughters got 5s on the AP exams, on the BC. I don't think they learned much. I gave them some of my college exams, especially in Calc 2. The BC calculus is not equivalent to any Calc 2 course that we're teaching. That's my experience. So yeah, I hear you, America. That's rough. We're glad you're still with us in math. Right.
All right.
Comments. I guess I'll turn it over to Chris.
To Chris or to me? Which one?
I've been calling Mike Chris for 5 years. I had to do it one more time. Both of their faces. Chris has long hair. Mike has a little bit less.
I wasn't sure if that was intentional.
I don't think it was. That is
great.
so funny. Sorry. This is an inside joke between the three of us. Anyway, thank you, Bob, so much. I'm glad all of you stuck around a little late on this Friday afternoon. Have a great weekend. Have a great rest of your semester, everyone. And let's hope we're back into some semblance of normal this summer or maybe even this fall. Thank you all for coming.
All right.
Have a
Thanks,
great one.
You too.
Thanks so much.
Bye.